Let's talk about derivatives now. So we're going to use our knowledge of uh, unit circle to kind of help us with some things with polar coordinates, but other times we're going to use parametric. So it really just depends on what the problem's asking us to do. So this first one says, given r equals 17 sine of 5 theta, find the rate of change of r with respect to theta at theta equals pi over 30. So we're looking at something with respect to theta, so we don't need to do anything special for our function here. So we want to take the derivative of r, dr over, with respect to theta, dr over d theta. So we're taking the derivative of our function like we normally would. So we have 17 times the derivative of sine of 5 theta times the derivative of 5 theta. If we put this all together, this is 85 cosine of 5 theta. So now that we have this, we need to find what it would be at pi over 30. So I have dr over d theta at theta equals pi over 30. We have 85 cosine of 5 times pi over 30. Okay, so 85 times cosine of 5 times pi over 30, or 5 pi over 30. The 5 and the 30 have a common factor, so I'm going to divide both the top and bottom by 5. This leaves pi on the top and 6 in the denominator. Pi over 6 is one of our unit circle values. It's that 30 degrees. And at 30 degrees, or pi over 6 radians, the cosine is the square root of 3 over 2. So we have 85 times the square root of 3 over 2. Depending on what we want, I can leave it like this, or I can keep going. 80 divided by 2 would be 40. 5 divided by 2 would be 2.5. That doesn't really give us a nice fraction, so we can leave it as 85 square root of 3 over 2. But there's really not a lot to do with it, unless we have a calculator that we can figure out what the actual number would be. But if we have a problem that says, given r equals 17 sine of 5 theta, find dx over d theta and dy over d theta, we have to find the parametric functions that we would be looking at in order to do this. Thankfully, we already found x and y, so I know that's r times cosine, so 17 sine 5 theta times cosine, and 17 sine 5 theta times sine. So I need to take the derivative of each one of these with respect to theta. So dx over d theta. One thing that I need to be careful with is that we're going to be using product rule here because we have sine of 5 theta times cosine. So I have the multiplication of things with variables. So the first part, 17 sine of 5 theta, is the first part of our derivative, u prime times v. But we already did some of that above. So 17 sine of 5 theta, we did the derivative of that, which is 85 cosine of 5 theta. So I'm going to go ahead and write that. Cosine 5 theta times its original, so times cosine theta, plus the derivative of cosine theta times the original of 17 sine of 5 theta. And if I need to simplify or not with this is kind of how I decide what I want to do with this. I can't really simplify this a lot because our angles are not the same. 5 theta and theta are not the same, so we can't really combine those. So it just kind of is what it is. And then I do the same thing, but with dy over d theta. And we're in the same boat, so we have to use product rule here, except for we have sine times another sine. So we have sine of 5, 17 sine of 5 theta times sine of theta. So the derivative is this first part, 17 sine of 5 theta is derivative cosine of 85 cosine 5 theta times the original of the second part, sine of theta, plus the derivative of sine of theta, which happens to be cosine theta, times the original of that 17 sine 5 theta. So it only gets a little bit more complicated when we have a radius that's not just a number. If our radius is just a number, that means that we are looking at a circle with a radius of whatever it told us. When we get to things that look like this, a little bit more complicated, we have what we call polar functions, polar graphs. And circles are a part of it. It's just the less complicated version of it. So that's something we're going to look at a little later, just not yet. So when we get to integrals, we'll look at that. Okay, so given r equals 4 plus sine of theta, find the rate of change of r with respect to theta, and find the rate of change of x with respect to theta. So the big thing that we're going to want to think about here when we're doing these problems is just like what it's asking. When we're looking at this, the rate of change of r with respect to theta and the rate of change of x with respect to theta are not like the worst things ever. We just have to be aware of what we're solving for. So we want dr over d theta, and we want dx over d theta. Dr over d theta, we're just going to take the derivative of what we have straight up, and we're done. Dx over d theta, we need to find what x is, and then take a derivative. So just a derivative, and find x, then take the derivative. So if we're looking at r, dr over d theta, we're taking the derivative of r equals 4 sine theta. The derivative of 4 is 0. The derivative of sine of theta is cosine theta. So dr over d theta is done. I need to find x, and I know x is r times cosine theta. Well, r in this case is 4 plus sine theta. So we're looking at 4 plus sine theta times cosine theta. I can take the derivative as is and use a product rule, or I can distribute what I have out and then take the derivative of what I have. Looking at or thinking through what would happen if I were to distribute this, this would be 4 cosine, which wouldn't need anything special, but then we would have sine of x times cosine x, which means I would need to use product rule. I do need to use product rule already because of this multiplication, so I'm just going to go ahead and do the derivative as is. So if we look at this, dx over d theta, the derivative of 4 plus sine of theta is just cosine theta, 0 plus cosine theta. We multiply by the original of the second function, which in this case is cosine, plus the derivative of cosine, which is negative sine, times the original of this first part, 4 plus sine theta. So if I really wanted to, I could simplify this to cosine squared theta minus, and then I can distribute this sine. So I have 4 sine theta minus sine squared theta. If I were to do this the other way, multiplying it out first and then taking the derivative, I'm going to get the same answer. I might just everything just depends on what we see first, how fast we need to do it, and everything like that. So all of this is just taking the first derivative. We're going to have to look a little bit more into taking the derivative with respect to x versus with respect to theta. So just like parametrics, if I want to take the derivative with respect to x, I'm going to have to do a little bit more work. So In the next little bit, we're going to talk about both dy over dx and second derivatives and what that looks like.